Greetings and welcome to the presentation of our paper entitled H-infinity control tuning to guarantee the output performance of linear time-invariant second-order systems. The outline of the presentation is first, introduction, second, motivation, third, main results, fourth, simulations and experiments, and finally, conclusions. Let us start with the introduction. Some preliminaries in H-infinity control theory for linear time-invariant systems are given. Here we have the H-infinity norm of a transfer function g. For instance, consider a second-order system defined as we can see here, where W is the natural frequency and theta is the damping ratio. S is the complex variable. A Bode diagram of this transfer function g is given in this figure for a Wn equals 1 radian per second and theta equals 0.15. In this axis we have the frequency in radian per second, and in this axis we have the magnitude of g. If you see here, for 1 radian per second the magnitude of g reached its maximum value, so this value is the H-infinity norm of g. We continue with the second-order system step-time response specifications. Consider one more time the transfer function g, defined by the natural frequency Wn and the damping ratio theta. Here we show the step-time response of a second-order linear system. The step-time response specification are the rise time, which is the time required for the waveform to go from 0.1 of the final value to 0.9 of the final value. The settling time, which is the time required for the transient damped oscillation to reach and stay in a band of plus minus 2%. And finally, the percent overshoot, which is the amount that the waveform overshoot the steady state or final value at the peak time, expressed as a percentage of the steady state value. Notice that the system's speed response is proportional to the natural frequency, and the overshoot is solely determined by the damping coefficient theta. Now I would like to introduce our motivation to develop this research. Consider, for example, a process having a critical time response, a coal-fired unit that demands strict time response specifications. In particular, I will concentrate my efforts here in the boiler. High level in the boiler can lead to water bubbles to pass through the system and impact on the turbine's paddles with catastrophic consequences. Also, high pressure in the boiler could lead to explosion with respective damage on personnel. Both variables are sensitive to a step command inputs. That's why it's so important to design properly the controllers in order to achieve step time response specifications according to the safety rations of operations. Our main results are shown next. Consider a second-order linear time-invariant system represented by these equations. Notice that we are measuring the hold state, and this system G can be expressed in matrix form by these matrices A, B1, B2, C1, and T12, where row 1 and row 2 are design parameters. What's the objective of our design? To find P epsilon such that it satisfies the algebraic equation, this one here, and also that the closed loop system with U equals minus B2 transpose P epsilon x warranties a decided setting time and percent overshoot. To this end, let us consider P epsilon as a square 2 by 2 matrix, positive, definite, with entries P11, P22, and P. The unperturbed closed-loop system has a characteristic polynomial equation as shown in 1. Notice here 2 entries of the matrix P epsilon. Now we want to establish some settling time and some percent overshoot required for the system to function properly. From these values we get natural frequency decided and damping ratio decided. If we consider with these parameters a decided characteristic of polynomial equation as in 2, and we match each coefficient of these two polynomials, we get 2 entries P22 and P of P epsilon matrix. So the first result appears. We have P22 and P, 2 of the entries of the matrix P epsilon. Of course, if we want to P22 and P be positive, those conditions here, these conditions here, must be fulfilled. From the algebraic Cartier equation, a set of algebraic equations arises, as shown here. From here we get rho 1, rho 2, P11, and gamma, the remaining parameters to complete the design. The second result is clear now. We have rho 1, rho 2, and P11. Rho 2 and rho 1 are real values if gamma satisfies that is greater than these two values here. And P11 is positive if gamma is also greater than this value. Moreover, P epsilon is positive definite if gamma is greater than this value. As a conclusion, P epsilon is positive definite and satisfies the algebraic Cartier equation if and only if gamma is greater than the 4 values previously shown. So the second result is complete. We have the remaining design parameters completely selected. Summarizing, find P22 and P as shown here, and you will get decided settling time and decided percent overshoot. Choose gamma greater than the 4 value that we shown. Finally compute rho 1, rho 2, and P11, and the design is complete. Simulations and experiments are shown next. Consider the equation of motion of a DC motor as here, where q is the position of the rotor, dot q is the angular velocity, wq is a coupled disturbance satisfying the bounded condition, and tau is the applied torque to the motor. Our motor has parameters like inertia and viscous friction coefficient as shown here. The control input tau is proposed as here, which yield this system. Notice that we have here a second order linear time-invariant system in the presence of our control input U. Our system can be expressed then in the H infinity standard form with A, B1, B2, C1, and D12 as shown here. Notice that we have rho 1 and rho 2 as design parameters. The first simulation, we would like to get a settling time of 0.1 second and an overshoot of 0.1%. Applying the methodology, we get rho 1, rho 2, and gamma, and figure A shows the step time response. We start at 1 radian and we want the system goes to the origin. Notice here that the settling time is 0.1 second and the percent overshoot is 0.1. So we achieved what we were looking for. here we show the control input necessary to get this results. In simulation 2, we change a little bit, decided the specification of a step time response. We want 0.2 seconds of setting time and an overshoot of 2%. Applying the methodology, we get row 1, row 2, and gamma. Figure A shows the step time response. Here we have 0.2 seconds of setting time and a 2% overshoot. One more time, we achieved the decided specification of the step time response, and this is the control input required. We perform a third simulation with a settling time of 0.2 seconds and percent overshoot 2.0. Applying our method, you will get row 1, row 2, and gamma. In this case, we have a perturbation present in the system. Figure A shows the step time response. Here we have the settling time was indeed 0.2 and the percent overshoot was indeed 2%. The control input is shown in figure B. In the streaming area, we can see how the control input attenuates the effects of the disturbance. In the fourth simulation, we consider uncertainty on the parameters. So we took inertia and the viscous friction coefficient and changed its values by 5% up and down. And that's what we can see here in all these colors. In the zooming area, we can see that no significant change is appreciated. Also, the control input have no significant change. So we achieve our goal. We also perform some experiments on a DC motor. Our experimental setup is shown in this figure, where we have the motor driver, and hardware in the loop from this space. In the first experiment, we tried to reproduce the same results of the first simulation. We also want a setting time of 0.1 second and percent overshoot of 0.1. Applying the methodology, we get row 1, row 2, and gamma. And in figure A, we show the step time response. Notice that the setting time was 0.1 second and the percent overshoot was near to 0.1%. In figure B, we show the control input in this case. For the second experiment, we tried to reproduce the results that we get from the second simulation. So we also want a setting time of 0.2 seconds and percent overshoot of 2%. Applying methodology, we get row 1, row 2, and gamma. Figure A shows the step time response, and figure B shows the control input. As we can see here in the second experiment and also in the first experiment, the results are not accurate in comparison with the simulations. One justification is we are dealing with a real process where nonlinearities are present. Finally, we would like to present some conclusions. We have presented formulas to tune a linear H-infinity controller to meet an LDO gain inequality constraint and to achieve the desired step time response specifications for second-order linear time-invariant systems. The simulations and experimental results corroborated the theoretical development. This paper represents the first step towards the synthesis of nonlinear H-infinity controllers satisfying required step time response specification for a second-order plant. As open topics remains the potential extension to higher-order systems, including more poles as well as zeros and or time delay. Thank you so much for watching this. We left some contact information for you at the bottom of the presentation. Thank you one more time.